The fundamental theorem of line integrals is the topic here, one of the topics in this section. To here deal with the idea of a conservative vector field and how that is associated with this notion of independence of path. Here we introduce the fundamental theorem of line integrals. You recall from Calculus 1 that we had the fundamental theorem of calculus, parts A and B. If we could combine those two into line integrals, you would have the fundamental theorem of line integrals. The first fundamental theorem of calculus showed us how to evaluate a definite integral by our lower and upper limits of integration. The second aspect of the fundamental theorem of calculus gave us the idea that if you take the derivative of the integral, you get the function inside. That is, that the integral and the derivative are inverses of each other. And so the key there was to pull out little f, the function. The fundamental theorem of line integrals here says that if you know that capital F is conservative, that is, that the energy somehow is conserved within the region R, and if M and N are continuous, it would have to be continuous to be able to find each point along the line to be able to evaluate. If capital F is conservative, then the line integral can be computed by just simply evaluating the potential function. And this little f here is the potential function. And so what this equals out to is the potential function f of x of t, comma, y of t, here evaluated as t goes from A to B. So that's the key to the fundamental theorem of line integrals. If you know that capital F here is conservative, then you can jump, instead of having to compute the line integral directly, just find the potential function. Just find a little f, and we'll use our method to find little f, the potential function, and then just evaluate it here. Now, understand that when you do the evaluation, depending on the problem, you may have to convert x to x of a and y of a, where here and then x of b and y of b, where a and b depends on t, right? That t hovers between the interval from a to b. So you want to be very careful about that. What does that mean? Well, to tell you the truth, it's possible that the function can end up looking like f of t, where t is evaluated from a to b. Sometimes the function may be left in terms of x and y, and so you can evaluate the potential function using that. And then sometimes you have to convert the x and y to the parameter t. We'll have some problems like that, and we'll show you. Now, if f is conservative, then also f is said to be independence of path. What does this mean? Independence of path says that, here the key is that f is conservative. The energy is conserved within the region. If that's the case, then it doesn't matter if you're moving from one fixed point to another fixed point. If you move along this path, and say, for example, if you call that c sub 1 for that curve, or if you move along this path, call this c sub 2, or if you move here along this path, let's call that c sub 3, then if when you compute the line integral going on C1 from some fixed point A to some fixed point B, or if you go along C2, go along C3, if they're all the same, then we say that the line integral is said to be independent of path. Well, one key to help you to determine, instead of trying to find each line integral along the different paths, C1, C2, and C3, is to find out if capital F is conservative. If capital F is conservative, then automatically the line integral is said to be independent of path. And so that simply helps us to know that you don't have to compute all of the line integrals of different curves if you know that you're going from one fixed point A to one fixed point B. That's the key. Now, the region R has to be what we call connected. That is that you can't have any jumps. You can't go out of the region and then to come back in to get from point A to point B. So here, a region must be connected in order for that region to be independent of path, or that line integral to be independent of path on the region. So here a region in the plane is connected when any 2 points in the region can be joined by a piecewise smooth curve lying entirely within the region. Now here down below are some examples of this. That here for this example, R sub 1 is connected because the path C is lying entirely within the region. To go from A to B here, you go out the region and then you come back over here, and so R2 is not connected. And so notice here that you can break the curve up into 4 different paths, all connected, which is fine. And so that's a connected region as well. So if that's the case, if F is continuous on an open connected region, then the line integral is independent of path. Watch this, if and only if F is conservative. So in other words, if F is conservative, then automatically it's going to be independent of path. If the line integral is independent of path, then automatically it's conservative. So if you know one, you know the other. If you know one, you don't have to even find the other because you get the other for free. Okay. It's almost like, you know, when you marry your spouse, you get her parents or his parents for free, independent of path. Anyway, crazy example. Let's look at some problems. I get in trouble when I do a lot of talking. Oh, before we get to the problems, I think a very cool thing here is that a curve C given by R of t is closed on this interval from A to B if R of A is equal to R of B. There's a drawing down here that helps us out with that. You see this curve here, this path, that it's a closed path. Notice here that that R of when you investigate this R of t at this point, you're going to get 0. Then you investigate it over here at this point, you get 0 as well. So it's a closed path, and if it's closed, then we say that the energy that's exerted there is 0. And it'll take Dr. Goldman to give his very famous illustration in his physics class about having some guys work for him. They're moving the furniture from his, I think, apartment to the house. And so he promised them that, you know, he'd get them something to eat and something to drink and pay them, you know, if they do the work. And so they start at the apartment, they take the furniture to the house, and then they come back to the apartment where they got to get their car. And so since the path is said to be closed, then the energy that is given from that path is said to be 0. And so Dr. Goldman said, I owe you nothing because technically you didn't do any work. Well, I tell you what, depending on the size of those guys, you may want to give them a couple dollars, even if they've done 0 work. But anyway, all humor aside, I wanted to look at this theorem 15.7 as a conclusion of this section where the conditions said to be equivalent. All of them, the key to this would be the vector field being conservative. If the vector field is conservative, then automatically you get for free that the line integral is independent of path, and the line integral is equal to 0 for every closed curve in R. That is, that when R of A is equal to R of B, and sometimes if it's a graph, if the graph is connected completely along that curve, you're going into it may not be a circle, but a closed path. You know, we're used to investigating paths from A to B like that. But what if you have that? Well, here the line integral is equal to 0 for this for this particular region, right? Well, no subscript there. Let's look at some problems. Find the line integral. If f is conservative, the integration may be easier. That is, use the fundamental theorem of line integrals. So this is m, this is n. So the partial of m with respect to y is 2x. The partial of n with respect to x is 2x. So here, too many dots. F is conservative. So if f is conservative, then we're going to find the potential function. To do that, we're going to integrate capital F, 2xy, replace the I with dx, plus the integral of x squared, replace the j with dy. Well, this gives us x squared y plus x squared y plus some constant. Here, for the potential function, you take 1. You delete the other repeating terms, right? So little f of xy is equal to x squared y. So for part A, we're going to find this line integral of f dot gr. Without computing that, we're going to just look at the potential function and evaluate that here as t goes from 0 to 1. But what is x and what is y? Well, it is given from here r sub 1 of t is the way it's defined. This is x of t of I plus y of t of j. Now the problem has this, that r of t is equal to ti plus t squared j. So do you get it? X is equal to t, and then y is equal to t squared. So we come here, x is equal to t, so this is t squared. That's supposed to be a 2. And then y is here t squared. So t, now you can evaluate t. So this is t to the 4th, evaluated from 0 to 1. We get 1. And what about part B? The line integral of f dot gr is evaluated by the potential function. T goes from 0 to 1. Now for this one, x is t and y is t cubed. Here we had x equal to t and then y was t squared. Can't see that. So here for part B, x equal to t, y is equal to t cubed. So x equal to t, so this becomes t squared, and then y is t cubed. So we get t to the 5th evaluated from 0 to 1, and that gives us 1. If it's independent of path, then it doesn't matter what path you travel along, you're going to get the same value for the line integral. Right? Well, how do you know if it's independent of path? If it's conservative. See, they're all equivalent. Right? And we found that f was conservative. Let's look at number 13. So for this one, m is equal to y and n is equal to negative x. It's not conservative. Why? Because the partial of m with respect to y is equal to 1, and the partial of n with respect to x is negative 1. So here it's not conservative. So all that stuff we just got through saying doesn't work for this problem. So for this one, you have to do what we did back in the previous section to find the line integral. So for part A, r of t is equal to ti plus tj. You need r prime of t, which is I plus j. And so for part A, x is equal to t and y is equal to t. Looking here, x is equal to t, y is equal to t. So for the line integral of f dot dr, this is the line integral from 0 to 1. F is yi minus xj, but y is equal to t and x is equal to t. So here, this is ti minus tj dot product with r prime of t. Remember, dr is r prime of t dt. So r prime is I plus j dt. So this is the integral from 0 to 1. Take the dot product. We end up with t minus t dt, and that gives you 0. What about part B? Here r is defined as ti plus t squared j, 0 less than or equal to t, less than or equal to 1. So we need r prime of t, that's equal to I plus 2tj, and x equal to t, and y is equal to t squared. This is the line integral. Well, we know the curved path is going from 0 to 1. This is fine. This is the integral from 0 to 1. F is yi minus xj, but y is t squared. So this is t squared I minus x, that's t j, dot product with r prime, that's I plus 2t j dt. Simplify that line integral. So this is t squared minus 2t squared. And so this gives us, when we integrate, 1/3. Sorry. This is negative the integral from 0 to 1 of t squared dt. And so now this gives us negative 1/3 t cubed. That's evaluated from 0 to 1. And so that just gives us negative 1/3. Now what about part C? R of t is equal to ti plus t cubed j. Here t goes from 0 to 1. So r prime of t is equal to I plus 3t squared j. And so the line integral of f dot dr is equal to the integral from 0 to 1. Here the function, the vector field, x is equal to t and y is equal to t to the third. And so this is yi minus xj. Well, y is t to the third, I minus x, that's t, j, dot product with r prime. So this is I plus 3t squared j dt. This is the integral from 0 to 1. We get t cubed minus 3t cubed. The dot product gives us a scalar, not a vector anymore. This is negative 2 times the integral from 0 to 1 of t cubed dt. So we integrate there. So this gives us negative 2 t to the fourth all over 4. T is evaluated from 0 to 1, which gives us negative 1/2. Let's look further. See how interesting it is that you see how it took us longer. You looked at number 11 and we determined that f was conservative. And so being that f was conservative, we got the answer, the result, a whole lot quicker. Look at part B, or number 13, that is. Number 11, f is conservative. Quick to get that. Number 13, f was not conservative. So it took us a longer time because you had to actually work out the line integrals for parts A, B, and C. Well, let's look at this problem. And we hope that here f is conservative. Well, let's examine. So here, m is y squared. The partial of m with respect to y is 2y. N is equal to 2xy. The partial of n with respect to x is 2y. Yay! F is conservative. So if that's the case, then we find the potential function by taking the integral here with this first part with respect to dx plus the integral with respect to dy, 2xy dy. Here the line integral is written in differential form, right? So either it can be written in vector form or it can be written in differential form. What's the differential form? Is that the line integral is said to be m dx plus n dy. That's the same thing as the line integral of f dot dr. One form is vector notation, the other form is differential form. Right? Both are equivalent. So we integrate here, we get x y squared plus 2x y squared divided by 2, which is x y squared plus some constant. So we're going to take the potential function, little f of x, y. We delete one of those guys, right? Or we delete the repeat and just keep one. So we just have here x times y squared. Well, that's all we need. So for part A, you want to compute the line integral. I'm trying to see where I can squeeze it. I guess I'll put it down here. So part A, the line integral of, oh, this guy's written like this, m dx plus n dy. So dy. So this is equal to the potential function, which was x y squared. X y squared. Here, now, so the terms for x and y, they go from 0, 0 to 4, 4. Now you can break that up into two paths. You can look at from 0, 0 to 3, 4, then from 3, 4 to 4, 4. So you have two of these guys, you get the same thing. How do I know? Already done it. Clean this wood. Anyway, so this is 4 times 4 squared minus 0 times 0 squared. You just get 64. About part B, part C, and part D. Part C and D, you can tell that they're closed, right? Closed curve. So the line integral will come out to be 0, right? We said that for a closed curve, the line integral is 0. You remember that? Let's see, where do we put that guy? For every closed curve, C and R, the line integral is 0. So we're going to use that to our advantage. Now, it's the same thing happening for part B as well. Here, this line integral, you can see it here. This is equal to, we got x y squared. That's evaluated. Here we're going from -1, 0 to 1, 0. Since y is 0 on both of those, you get 0. Well, it's closed. Here's a closed path. So part B, part C, closed. The line integral is 0. Part D, closed. We get 0. Hate to drag this out, but let's see if I can work this as expeditiously as possible. The time is of essence. So find the line integral here. M is 2xy, and n is x squared plus y squared. Find the partial of m with respect to y, so we get 2x, and the partial of n with respect to x is 2x. So it is conservative. So we found the potential function, so we integrate 2xy with respect to dx plus the other one here with respect to dy. So this gives us x squared y plus x squared y plus 1/3 y cubed plus c. Delete this guy. And so we keep everything else. So our potential function, little f of xy, is equal to x squared y plus 1/3 y to the third. It's conservative, so it's independent of the path. So it doesn't really matter about the path. All you need is the fixed points from where I'm coming from to where I'm going. That's important. Oh, wow. Theologically sound. It's interesting. All of us have different paths, but the key is where you started from and then where'd you go, right? Sometimes it doesn't matter about where you start. What matters is where you're going. And everything in between, I mean, that's incidental. It's different for all of us. But you can end up in a good place if your vector field is conservative. Oh boy, that's something right there. Okay, part A. So here, this line integral defined as a differential is equal to the potential function evaluated from 5, 0 to 0, 4. Right? So we plug in x equals 0, y is 4 plus 1/3 4 to the third minus 5 squared times 0 minus 1/3 0 to the third. And that just gives us 64/3. Now, do we get that same answer for part B? Part A, you're moving along an ellipse. Part B, you're moving along a parabola. What happens? Let's see. We evaluate this again with the potential function because it's conservative. Here we're moving from 2, 0 to 0, 4. And so we plug in here, x is 0, y is 4, plus 1/3, 4 to the third, then minus. Do you see that it's going to be 0 when you plug in here y to be 0, y to be 0 there, so it's just minus 0. So this is still 64/3. It's conservative, so it's independent of the path. The line integrals all must be the same. I'm going to go ahead and finish this right now. So that problem, well, it's kind of long, but I'm just going to do part A. We'll omit part B. So this is a vector field in the space. And so since it's in the space, we have to use the curl to determine whether or not it's conservative. Let me check my time. 34 minutes. Maybe we can end at 40 minutes, so hopefully that's okay. So we put m 2y plus x. We'll put y, x squared minus z, and then z, well, p, 2y minus 4z, m, n, and p. So we delete the ith row and column, so it's the partial of this term with respect to y. That's 2 minus the partial of this term with respect to z. This is minus 1, so this is minus a minus 1 is plus 1. We go to the jth position, and we delete the jth row and column. So is this partial over here with respect to x? 0 minus the partial of this guy with respect to z, that's 0. And so then we look at here the kth position. This is this partial here with respect to x, so that's 2x, minus this partial with respect to y, that's minus 2. Just go back, make sure that everything was right. For the first one, deleted the ith row and column, so it's this partial with respect to y, that's 2, minus this partial with respect to z, is minus a minus 1. So that looks fine. So the curl of f is equal to 3i plus 2x minus 2 equal to k. It's not equal to 0. This implies that f is not conservative. So since f is not conservative, we must find here this line integral by computing this directly. So we need to actually find f dot dr. Well, to do that, to get dr, remember we need r prime. Well, r of t, this problem is ti plus t squared j plus k. This implies that r prime of t is equal to I plus 2tj. So now this line integral of f dot dr is the integral. Here, do we know our endpoints from 0 to 1? We need capital F. F must be defined in terms of what x is, what y is, and what z would be. So for part A, x is equal to t, y is equal to t squared, and z is equal to 1. So we need that. And so here, the problem tells us that, I gotta write all this stuff, f is equal to 2y plus x. Well, y is equal to t squared, so this is 2t squared plus t. This was for I. Now we move here, the jth position. This is x squared minus z, but x is t, so this is t squared minus 1. That's my best friend from Ohio calling me, but I call him back. I'm busy. Just like Nehemiah, we're up on the wall and we can't come down, but he's not Tobiah or Sanballat. I wouldn't compare him. No, he's a great preacher that's calling me, and I want to talk to him when I get through with you. So, okay, so F is 2y minus 4z for k, right? Dang it, too much stuff. So 2y, y is t squared, so this is 2t squared minus 4. 2t squared minus 4. Okay, I think I got everything. Times the dot product with r prime. This is I plus 2tj. This is dt. Alrighty. This is the integral from 0 to 1. Do the dot product. Do the hokey pokey. So this is 2t squared plus t times 1. This is plus, that's the t. They look the same. What do? You just rewrite it. You rewrite it, they still look the same. But anyway, and then the dot product of t squared minus 1 times 2t. So plus t squared minus 1 times 2t. The integral from 0 to 1. So we simplify this. This is 2t squared plus t plus 2t to the third minus 2t dt. This is the integral from 0 to 1. 2t squared minus t plus 2t to the third. Now we integrate. So we get 2t squared over 2t cubed divided by 3, that is, minus 1/2 t squared plus 1/2 t to the 4th. Evaluated from 0 to 1. So we get 2/3 minus 1/2 plus 1/2, and that just gives us 2/3. All right, I think 2 more problems. I just do one of them. It's this number and then the one down there. They work exactly the same. What happens good for us is that if the vector field is conservative, then you get it. Now it says use a computer algebra system to verify your results. All right, don't worry about that. M is equal to cosine x sine y, and n is equal to sine x cosine y. The partial of m with respect to y is cosine x cosine y. The partial of n with respect to x is cosine x cosine y. So indeed it's conservative, right? So if that's the case, then we find the potential function by integrating directly. So we integrate here with respect to dx. So that gives us sine x sine y plus integrate over here with respect to y. That gives us sine x sine y plus c. We just take one of them, so our potential function, little f of x, y, is sine x sine y. So the line integral of what you're looking for, you can bypass that by just evaluating the potential function. Here we are evaluating from 0, comma, negative pi to 3 pi over 2, comma, pi over 2. So this becomes sine of 3 pi over 2 times sine of pi over 2 minus sine of 0 times sine of negative pi. That's 0 right there. And so sine of 3 pi over 2 is negative 1 times sine of pi over 2 is 1, then minus 0. So you just get negative 1. I'm going to stop there. Thank you. I've held you long enough.